Okay, so today we're going to start off the year with the very wonderful topic of water on topic 2.2. So you might be saying to yourself, hey, I'm in a biology class. Why are we talking about such a boring molecule? And the reason for that is that water is pretty essential to life. So our own planet is covered with 97% of our surface is water. And when we're looking for life on other planets, the first thing that we look for is liquid water. Right, so if we're considering, say, Mars, the reason that people were so excited about it is because they think they have these, solid ice, polar ice caps, and that there may be evidence of Mars having had liquid water on its surface at one time. And even in your own body, 60% of your own cells, so everything that makes you you, 60% of it is actually water. So then this might be the question, okay, what is so special about this little molecule? And I'll just tell you up front that there are certain properties of water that make it extra special, and I'll just go ahead and list them out right now because these are the properties that you're going to have to know and be able to explain. So they're just polarity, cohesion, adhesion, thermal properties, and solvent properties. So all of these together are what make water so important to life. So okay, let's think back now. Who remembers what is the chemical formula for water? So if you said H2O and you were able to draw a molecule, something like that, you'd be absolutely correct. And let's just take a sort of walk through memory lane back to chemistry class. And there was this property called electronegativity. So this is our periodic table here. And so electronegativity, if you will recall, is how tightly an atom holds, electrons to it. And this property, electronegativity, increases as you move from left to right on the periodic table, and it also increases as you move down the different columns. So overall electronegativity is going to increase as you move in this direction. So if we look at water, it's got two different kinds of atoms in it, right? It's got oxygen, and it's covalently linked to two different hydrogens. So between these two different kinds of molecules, which one do you think is going to hold onto those electrons more tightly? The oxygen, which is located more to the right, or the hydrogen, who's going to be greedy with those electrons? So if you guessed oxygen, you would be 100% correct. And what that will eventually do, because that oxygen is being greedy and it's holding onto those electrons, it is going to become more electronegative. Or it is more electronegative, so it's going to end up with a more partial negative charge because those electrons are negative, and if it's holding them more tightly, it's going to have a partial negative charge. And so what's also going to happen at the same time is because of that, because the oxygen is pulling those electrons away, the hydrogens in this molecule are going to end up with a partial positive charge. So when you have this sort of differential in charge in a molecule that has a special name, and that is polar. So a polar molecule is any molecule where you have this sort of separation of charge on the molecule due to a difference in electronegativity. And in this case, it's the oxygen that's pulling that negative charge, and then you end up with this positive, partial positive on the other end. So water, like many other molecules, is considered to be polar. You can also think of it as acting like a little magnet with like a north and south pole. Okay, so if you go back to thinking about your magnets, how do you expect charges to interact, or oppositely charges to interact? So how do you think a negative charge is going to want to interact with a positive charge? Do you think they're going to move away from each other? Or are they going to move towards each other, or are opposites going to attract? So just go ahead and take a guess now. Right, and then on the same note, how are similar charges going to move towards each other or interact with each other? If I try to put a negative and a negative together, are they going to want to be next to each other, or are they going to run away? So will similar charges move away from each other or towards each other? What do you think? So this polarity, right, is going to give you that difference in charge, and if you guessed that opposite charges are going to want to interact, you would be absolutely correct. So this negatively partial negative oxygen is going to want to interact with that partial positive hydrogen, right? So this is a rule of opposites attract. So if we have one water molecule here and a second one nearby, this one's going to rotate so that the negatively charged oxygen is going to interact with that positive hydrogen. And so these are special kinds of bonds. They're called hydrogen bonds. And this is basically the reason for every single special property of water. So if you ever get into a question in an exam and they say like, why does water have high specific heat? Why does water have, high latent heat of vaporization? The answer is going to be because of these hydrogen bonds, right? And this doesn't just happen once. It's going to happen every time that there is an interaction between the water molecules in that solution. So every single oxygen that's got a slight negative charge on it is going to want to interact with a slight positive charge on a neighboring hydrogen. So a hydrogen bond is going to form between the hydrogen of one water molecule that has that partial positive and the oxygen of a neighboring oxygen water molecule. And so on their own, these hydrogen bonds are very weak, but when they're all together, it makes water pretty strong and pretty stable. And again, this is the reason for most of water's special properties. It's going to come down to this hydrogen bonding between this partial negative oxygen and the partial positive hydrogen of a neighboring molecule. So let's talk for a second about cohesion. So if you think about the word cohesion, what does it mean to be cohesive? It means to stay together, right? If we're a cohesive group, we stay together. So if I were to say, I have this group of water molecules and they have all of these hydrogen bonds that are interacting with each other, if I were to say find a way to pull one away from the group, it's actually going to pull the whole network along with it. So cohesion is water's ability to bind to itself, right, which is what's always happening with these hydrogen bonds. The reasons that water is cohesive is because of those hydrogen bonds. So water is going to be sticky, for all intents and purposes due to those hydrogen bonds. And when you pull one water molecule, you're going to pull them all. So that's what it means to be cohesive, right? And you can test this yourself. If you, have a little bit of water and you pour some on your table and you stick your finger in it and you pull that water away, you're going to pull some water with it, right? That's because the water is holding on to, its other little friends because of this cohesion property. So cohesion is also what results in water tension, right? So these water molecules sticking together, those bonds are stronger than the weight that this bug is putting on it, right? And it's also the reason that if you take a penny and you drop little water droplets on it, you can put a bunch of them on there and it's not going to roll off the side because those water molecules are sticking together. They're stronger than, say, the forces of gravity pulling on the side there. So those hydrogen bonds give that a pretty strong cohesion reaction. So the next thing is adhesion. So water is going to stick to some surfaces, particularly other polar substances, right? So other things that have those slight charges on them. And cohesion plus adhesion is what causes that capillary action. So if I were to take, say, a paper towel and stick it in some water, you already know that that water is going to creep up by itself automatically. It'll go higher than the level of the water. And what's causing that is a mixture between cohesion and adhesion. So the water is going to just stick in particular to paper towels because it's basically a sugar molecule that's in there and it's polar. And while it's doing that, it's going to pull its friends up with it, with that cohesion molecule. So that's adhesion. So cohesion is water sticking to itself. Adhesion is water sticking to other surfaces. You know that if you stick your hand in a bowl of water, if you pull it up, it's not all going to immediately fall off. A lot of it is going to stick to you, right? So the last process that we're going to talk about here is transpiration. So this is how water is transported in plants. So you probably already known since grade school that water is going to enter the roots through capillary action. But what you probably haven't heard before is that plants they breathe out water vapor, really, right? So you have the water that's going to come in through the roots, and through capillary action it will go a distance up the stem. But the plants will also release water in the form of vapor and this is called transpiration. And when they do that, remember, water is basically like holding hands all the way down to the ground, and it's going to pull it up through cohesion. So once the water leaves through the leaves, it's going to pull up another column right behind it. So this is really important for water transports in plants. We'll talk more about that in the spring. So water has a number of really important thermal properties, particularly for aquatic organisms. So if I show you this graphic that I took a screenshot of, the temperature distribution is probably worse than this now. Do you notice something about the temperatures near the coast compared to how they are inland? Oh, hey, it has a little virus graphic there. Weird. So what you might notice is that the temperatures are cooler near the coast, and that's because water itself can absorb a lot of heat just by itself. So like some of the old school air conditioners, they used to just have people blow fans across, buckets of water because that would absorb some heat for you. And there's a good reason for that. And again, it comes right back to those same pesky hydrogen bonds. So remember, collectively, they are very strong, and it's going to take a lot of energy to break those hydrogen bonds apart. So let's talk about a feature called specific heat. So specific heat is the energy that's required to increase 1 gram of a substance by 1 degree Celsius. So how much energy do I have to put into this stuff to raise its temperature? If we look at liquid water, it has a really high specific heat of 4.18. And you do have to know that number. Like, you have to be able to recognize, like, if I ask you what specific heat of water is, you better spit out 4.18 joules per gram per, Celsius. So if we look at that and compare it to, say, the energy that's needed to raise the temperature of ice, it is far less energy. It's like half, right? So it takes you less energy to melt a cube of ice than it would be to, say, raise the temperature of a pot of water, which you can probably guess that, right? Like, you can melt an ice cube by just holding it in your hand, but you probably can't boil water by holding it, right? So liquid water takes a lot more energy to heat up. And then same thing with the water vapor. It's not that hard to raise the temperature of the air. So dry air by itself is only a quarter of the specific heat. So if I wanted to heat a room, that would take way less energy than me trying to like heat water. And I guess you could try to do this in your own house, like take the temperature of the air versus the temperature of, say, a bowl of water and see what that is. And the reason is that, heat is absorbed when those hydrogen bonds break, but it requires more heat to actually break them. So that is why liquid water has such a high specific heat. And that's really good for most of the organisms that live on Earth. So remember, 97% of our surface is water. Life started in the ocean. So having a water environment that's stable, right, in temperature is really going to be important. I don't know if you've ever had fish. Someone out there had fish. They're pretty easy to kill if they get outside a certain temperature range. So because the temperature of water is so hard to change, it takes a lot of energy. This is really good for those aquatic animals. So air temperatures can change really quickly, but the water, the big bodies of water, especially those oceans because they're huge, takes a tremendous amount of energy to change that. Okay, so that's the specific heat. So now let's talk about the latent heat of vaporization. So basically what this is the energy required for a molecule to evaporate, right? So water, just like the specific heat, has a high latent heat of vaporization. So it takes a lot of energy to make that happen. So when it actually evaporates, it takes a lot of energy with it. So it takes a lot of heat energy with it. So that is why we sweat, right? So when you sweat, your body puts a sheen of water all over you so that when it evaporates, it takes a lot of the heat with it. And it's the same reason that dogs pant, right? So they're putting all that liquid on their tongues, and when that evaporates from their tongues, it helps to cool their body down. So it's especially important for mammals. Okay, so now let's talk about water as a solvent, right? So this is the second to last property of water that makes it important, right? Water as a solvent. So what is something that you know does not dissolve in water? What does not mix with water? Right? What doesn't mix with water? So you might have said oils, right? And yeah, that's true, but do you know why? So let's go ahead and find out. So just a reminder, right? So water is polar. Again, it has this partial negative charge on the oxygen. It's got these two partial positives on the hydrogens. It allows it to form those, hydrogen bonds with itself, which it will do in solution. Um, Here's the thing. Water, like I said, is going to interact with any polar molecule, right? So there's no reason that, this negative oxygen here is going to blow off a positive charge on something else. It will interact with any polar molecule that has a similar, distribution of charges. And so there's a special word for that, and that is called hydrophilic. So hydrophilic is to be water loving, right? So hydro means water, philic means that you have, an affinity for it, that you love it. So all hydrophilic molecules are polar. So they're going to have, some either outright positive or negative charges on it, or they're going to have the partials like water itself. And those are going to interact with those positive and negative partial charges on water. And so what eventually is going to happen, so say you have a glucose molecule. And by next week, you're going to be able to draw this from memory. So this is a glucose molecule. And just like we see in water, all these OH groups, all these hydroxyl groups are going to have a partial negative on them, right? Because remember, oxygen is very greedy. It's very high in electronegativity. It's going to want to hold those electrons. And so the water is not going to see it any differently than another water molecule. So those partial positives on the hydrogens are going to want to interact with those kinds of partial charges. And so that's why you can dissolve like sugar in water, because sugar is polar. Or say something like this molecule. So this is the chemical formula for baking soda, also known as sodium bicarbonate. So again, we have a positive charge in that sodium that's going to be very appealing to those oxygens, right? And then, to those negative oxygens. And then it's got this negative carbonate that's going to want to interact with those partial positive hydrogens. So baking soda can be dissolved in water, again, because of this distribution. It's polar. Similarly, table salt. The formula is sodium chloride, right? And it's got this, it's an ionic molecule. So they have this distribution of charges. Once again, the negative oxygen is going to want to be friends with that positive sodium, and the chloride has a friend too. So water is going to form cages around these molecules, and that's why they actually dissolve. So any polar molecule that has this, again, distribution of charges will dissolve. So what about nonpolar substances? So this is going to be a lipid, which you'll get to know again next week, and you'll be able to draw these also. In comparison to the glucose, it doesn't have many hydroxyl groups. It only has the one. So it's mostly a bunch of uncharged carbons. And basically, this is something called hydrophobic. So again, hydro is water. Phobic, to have a phobia, means you fear it, you run away from it. If you have arachnophobia, you're afraid of spiders, right? So hydrophobic is water fearing. So for the most part, this lipid does not have any charge in atoms to interact with any of those partial charges on water. So it basically won't go into solution, because there's, the water is going to make friends with itself, and it's going to push out those lipids. So there's been talk, so this is a picture of Titan, which I believe it's one of the moons. I can't remember if it's Jupiter. I think it's Jupiter. And they have always kind of talked about this moon, hey, there might be life on there, because it has a lot of methane. So methane is important for a lot of ancient life here on Earth. So there might be a role for methane as a solvent. So methane might be another solvent for life. So other planets like Titan, technically not a planet, it's a moon, have liquid methane. And so just to compare the two, okay, we have our little water molecule here, right, with its partial negative and its two partial positives. Methane, in comparison, is just a carbon covalently linked to 4 different hydrogens. And compared to the water, it has no charges, right? It's non-polar. So just on that, how would you expect its specific heat, its latent, heat of vaporization, do you think this would be a weaker molecule overall, so have lower numbers, or a higher number like water? Yeah, okay, so this is nonpolar, so no hydrogen bonds. So this molecule overall is going to be less stable because it doesn't have the ability to make all those hydrogen bonds like water. So it will have, you would expect that it's going to have a lower specific heat, a lower heat of vaporization, kind of a lower everything. It's going to also melt and vaporize at lower temperatures. But in comparison, methane can dissolve nonpolar substances. So everything that, it should be able to dissolve, say lipids. So this is the last table because you do have to be able to compare water and methane. So water, remember, is polar because it has those distribution of positive and negative charges, whereas methane is nonpolar. Where water forms hydrogen bonds, which is the basis for all of these other features, it makes it strong, there are no hydrogen bonds that are forming in methane. And so if you predicted that all these numbers were going to be lower for methane, you would be correct. It has half the specific heat, in the liquid form. So what this means is that if I had an ocean of methane, it would take half the energy to change the temperature of that environment as water. So overall, it's going to be less temperature stable. This is almost like a third of the energy for latent heat of vaporization. So if an animal needed to cool itself and it sweated methane, liquid methane, it's going to have a harder time. It's going to have a less efficient way of doing that, of releasing that energy. And also methane only is liquid at really cold temperatures, so about minus 182, minus 182 Celsius. That's pretty freaking cold. Okay, so that concludes the 2.2 lecture, so be sure to finish up your Go formative from here on out. So next week we talk molecules to metabolisms and carbohydrates and lipids, so stay tuned.